In 8.1 and Math 31, we start to look at some exponential functions and a little bit later logarithmic functions. And basically, the reason this is in the notes is to remind you a little bit of basically the work that you've done in 30-1. We looked at exponential functions in 30-1, and that was in chapter 7. So again, if you want to, you can go back and maybe take a look at those videos. We're going to cover a lot of the same stuff. This wants us to graph the following functions, so I'm going to kind of color code them here. We'll do f of x equals 3 to the power of x in black. The way that I'm going to do this, I think the easiest way to do this is to talk about what happens when x is equal to 1. Right? If f of x is equal to 3 to the power of x, then when x is equal to 1, I'm going to have the point 1 comma 3. Another point that it's going to be on here is 0 comma 1. Now, I'm going to draw this, and maybe I'll draw it right now. Why not? Because it is exponential growth, it is not linear, so it's going to have that kind of upwards growth at the end there, and it is getting very, very quick, which we'll talk about a little bit later in calculus. I'm going to do f of x equals 5 to the power of x next. That is still going to go through 0 comma 1. Because anything to the power of 0 is equal to 1, but it's not going to go through 1 comma 3. If x is equal to 1, then 5 to the power of 1 is 5. So we get that point 1 comma 5 on our red graph, and then beyond that, it is actually going to grow quicker. And a good way to look at that is, if we looked at maybe the next point, maybe I'll just draw them over here. If we look at 3 to the power of x, yeah, it contains 1 comma 3, but then there's 2 comma 9, 3 comma 27, and I'll just do 3 dots there. If I looked at 5 to the power of x, we'd have 1 comma 5, but then I'd have 2 comma 25. That's a much, much bigger vertical gain when x is only increased by 1. So really importantly, that the base of our exponential function ultimately controls how quickly it increases. When we look at f of x equals 10 to the power of x, still going through 0 comma 1, but now it's going to go through 1 comma 10, somewhere there, and this will certainly grow very, very quickly compared to the other two. So that's a rough, just kind of easy sketch to compare these three graphs. And then what the bottom of your page asks us is to talk about some information of these graphs. And I would encourage you to look at the graph, and I'll take, I'll just kind of, I guess, vamp for a minute here. Look at that graph and see if you can answer the questions on the bottom. With, maybe pause the video, try it, and then check. I'm going to put the answers up here in a second, because it's really important that what we're doing here is trying to, come up with a cross section of graphs and then identify some common or maybe, uncommon themes within. All right, so there's your opportunity to pause it if you want to try that. It is a very, very valuable thing to do. I will do them here. So the x-intercepts of the graph do not exist. There are no x-intercepts for these exponential functions. You would have to have a vertical translation down for that to occur. The y-intercept for all three is at 0 comma 1, because anything to the power of 0 is equal to 1. My horizontal asymptote is at y equals 0. You cannot put a number to the power and get 0 unless it's 0, I suppose. The equation of the vertical asymptote does not exist. Really, really important. If you look back at those graphs, even though it looks like there might be a vertical asymptote there, those graphs will continue to increase as we go to the right. These functions are examples of, and really this should maybe have the option of, growth or decay, but these are exponential growth functions. When we talk about exponential growth or decay, we are talking about the behavior of the function as x increases. So because y is increasing, we call that growth, right? The value of the function is getting larger and larger is really what that's saying. All right, now what that means then is the limit as x approaches positive infinity will be positive infinity. Because those graphs, and I'll draw just a basic graph here, as x increases to the right, the graph is going to increase without bounds. So it's just going to get bigger and bigger and bigger. But the limit as x approaches negative infinity is going to go to 0. And that's where we see our horizontal asymptote at y equals 0 show up within the limit of this concept. All right, now I'm not going to belabor these as much as the previous. We could graph these three functions, and again, I'm not overly worried about this. You've done this in Math 30, but I am going to color code them. So 1/3 to the power of x is in black, 1/5 to the power of x is in red. They do have the same x-intercept still. And then the last one here would be 1/10 to the power of x, would look something like this, give or take, a little bit roughly for sure. And it's a very similar conversation to what we just did, except really importantly, the base of the exponential function is now in between 0 and 1. And I would really, really encourage you to go back, take a quick look at chapter 7 and in Math 30-1, sorry, don't look at the trig. That's not going to help you here. But if you look back at, the exponential chapter in Math 30-1, we are talking about a lot of the same thing, which is really, really important that we attach that meaning to this. Okay, and then the following information, the x-intercepts still don't exist. The y-intercept actually isn't changed. It's still at 0, 1. Our horizontal asymptote is still at y equals 0. There is no vertical asymptote. And then these functions are example of exponential decay functions. And then the limit as x approaches infinity, I'll draw that kind of sketch again, that we can picture what's happening. And I didn't draw that end very well, just extend it a little bit. That as x approaches positive infinity, the value of my function is approaching 0. But when x is approaching negative infinity, the value of my function is approaching positive infinity. One thing that a lot of students struggle with is that these exponential functions are never negative. So we'll see the value of our limits be positive unless there's a reflection or something of that. Now, I'm going to put the summary of the investigation in part 2 just so that we can use it for the rest of this section.